8.3 inverse function. We did cover this function in intermediate algebra and pCal. We're going to use this in calculus, but let's review the inverse function first, alright? I have a function f of x here. I'm going to find the inverse of it. So first thing you do, you write f of x as y. So you're going to have y equal cube root of x minus 1. Next step you're going to do, you're going to solve for x. So for me to solve for x, I have to cube both sides. So I'm going to have y to the cube equal x minus 1. Then you're going to solve for x, alright? So my x is going to be y to the cube plus 1. So first step, I solve for x. Next step, I'm going to interchange x and y because the inverse function is x become y, y become x. So I'm going to write x as a y and y as an x. So I'm going to have y equal to x to the cube plus 1. So this step I interchange x and y. Alright. Next step you're going to solve for y, but it's already have y by itself, so I don't have to do anything. But if you don't have y by itself, you will solve for y, and then you would write this as the inverse function. So this is my inverse function of f of x. Alright, so the definition said that if the two functions are inverse of each other, you would do the composition. F of g of x should be equal to g f of x, and they should equal to x. So let's show that they are inverse of each other. So I have f of x is equal to cube root of x minus 1, and let's call this g of x. Alright, so I'm going to do the composition. First I'm going to do g of f of g of x. So basically the g of x is the inside function of f of x. So I'm going to replace x to the cube plus 1 for g of x. So I'm going to have f of x to the cube plus 1. Now I'm going to go to my f function. Whenever I see x, I replace by x to the cube plus 1. So I'm going to have cube root. Instead of x, I'm going to have x to the cube plus 1. Alright, let's simplify this. Then I'm going to have cube root of x to the cube plus 1 minus 1. The plus 1 and minus 1 will cancel out, so you're left with cube root of x to the cube, which is x. Alright, so I prove this equal to x. That's not enough, you have to prove the other way around as well. So I have to show that g of f of x, alright, I have to show that equal to x. So now the f function is the inside, the g function is the outside. So I'm going to replace f of x with this. So I'm going to have g, instead of f of x, I put this in. Alright, now I have a g function. You go to the g function. Whenever you see x, you replace by this. So instead of x, I have to replace by this. So it's cube root of x minus 1 to the cube plus 1. Alright, then I will simplify this. So this just turned to be x minus 1 plus 1 from here. Simplify this, I have x. So I did check both directions equal to x, so they are inverse of each other. Alright, let's see next example. Hi everyone, let's look at our next theorem. Theorem 5.7, the existence of an inverse function. The first condition, the theorem said a function has an inverse function if and only if it is 1 to 1. So 1 to 1 is mean you have one x has one y. Alright, or you can do the horizontal line test. It should intersect the graph only one time. And the word if and only if mean if this is true, then this is true. And if it's the other way around as well. So if the function have an inverse, then it's 1 to 1. And if it's 1 to 1, it has an inverse. It go both direction when you have the statement if and only if. The second one is say if f is strictly monotonic on its entering domain. Strictly monotonic means it's either increase the whole interval or decrease the whole interval, not increase and decrease and increase and decrease. So either increase the whole interval or decrease the whole interval. Alright, so if f is strictly monotonic on its entire domain, then it is 1 to 1 and therefore it has inverse function. So let's look at our example. Use derivative to find if the graph is strictly monotonic and has its inverse. So if it is strictly monotonic, it has an inverse by definition. So let's look at f of x is equal to x to the fourth over 4 minus 2x squared. I will take derivative of this and bring the 4 up front, and the degree reduced by 1, and the 4 cancel out, so have x to the cube minus 4x. I bring the 2 here, so minus 4x. So this is the derivative of a function. Next step I'm gonna do, I'm gonna set it equal to 0 and solve for x. So I have x to the cube minus 4x. I factor out the x. I left with x squared minus 4. This is difference of square. So I can write it as x times x plus 2, x minus 2 equal to 0. Set it equal to 0. Solve for x. So you have 3 things multiply each other. 1, 2, and 3. So one of them have to be 0. X, or all of them can be 0 as well. So if x equal to 0, we have x equal to 0. If x plus 2 equal to 0, then x equal to negative 2. If x minus 2 equal to 0, then x equal to plus 2. So I have 3 critical number, 0, plus and minus 2. So I put them in a number line. So this negative 2, 0, 2 divide the region into 1, 2, 3, and 4 region. You have to test. This case I didn't test all of them because I don't need to. All we need to test that is increase the whole thing or not increase or decrease the whole interval. So I picked the first interval here is from negative infinity to negative 2. You can pick any number. I pick negative 3 in here into the derivative function. So negative 3 to the third minus 4 times negative 3. I end up with negative 15, which is negative number. This means this interval is decreasing. And I pick the last one. I have 2 here, so I can pick anything between 2 to positive infinity. I pick 3 to the cube minus 4 times 3, I get 15, which is plus, which is mean increasing. You can do this too, but unnecessary because it's already shown that this is decreasing, this is increasing. So it's not strictly monotonic on negative infinity and infinity. Therefore, f, the function, does not have an inverse, right? So let's look at the next one. All right, I have f of x is equal to 2 minus x to the cube. I take derivative of constant, which is 0, derivative of minus x is minus 1. Derivative of minus x to the cube is minus 3x squared. Now, for any x at all, any x, if you square it, it's going to be positive. Positive times negative 3 is going to be negative number. Negative number and negative 1 is going to be negative. So any number, for all x, is going to be negative, which means that f is decreasing on the whole negative infinity and positive infinity. Therefore, f is strictly monotonic and has an inverse. Alright? We just finished 4.3. I'll see you next time. Bye.